Welcome to today's session. In this video, we'll explore problem number 1436, Destination City. This is an interesting problem that focuses on identifying a unique city in a given list of paths. Stick around as we break it down step by step, discuss different approaches, and arrive at an optimal solution. Let's get started. Here, we are tasked with solving a problem involving a series of paths connecting cities. The input is an array called paths, where each element represents a direct connection between two cities, city_A and city_B. The goal is to identify the destination city, which is defined as the city that has no outgoing paths. The problem guarantees that the graph of these paths forms a single continuous path without any cycles. In other words, every city except one will have both one incoming path and one outgoing path. The destination city is unique because it only has an incoming path and no outgoing connections. The input consists of a list of pairs, where each pair specifies two city names. The output is a single string, representing the name of the destination city. Let's walk through some examples to understand this better. In the first example, the input is a list of paths: London, New York, Lima, Sao Paulo. The output is Sao Paulo. To understand why, we can trace the connections. The path starts at London, which leads to New York, then to Lima, and finally ends at Sao Paulo. Sao Paulo is the destination city because it has no outgoing paths. In the second example, the input is B, C, D, B, C, A. The output here is A. By following the paths, we see the sequence: D leads to B, which leads to C, and finally to A. Once again, A is the destination city because there are no paths leading out of it. Expanding on the second example, the sequence of connections is clearly D to B, B to C, and C to A. As A has no outgoing paths, it is confirmed as the destination city. Now, consider the third example, where the input is just a single path, A, Z. The output in this case is Z. Here, the path is straightforward: A leads directly to Z, and since Z has no outgoing paths, it is the destination city. These examples illustrate how to identify the destination city by tracing the paths and determining which city lacks any outgoing connections. Finally, there are a few constraints and edge cases to consider. The number of paths, n, will range from 1 to 100. Each path contains exactly two cities, and the lengths of the city names will be between 1 and 10 characters. The cities in any given path are always distinct, and their names consist of uppercase and lowercase letters, as well as the space character. Importantly, the graph of paths will always form a single, continuous path without cycles. For edge cases, if there's only one path, the destination city is simply the second city in that path. For multiple paths, the destination city is the one with no outgoing paths. Additionally, the solution must handle city names of varying lengths and character cases correctly, ensuring that the output is accurate regardless of these variations. This guarantees that the problem can be solved efficiently and correctly under all valid inputs. To solve the destination city problem, let's first consider a brute force approach using iterative search. The intuition here is straightforward: the destination city is the one that lacks any outgoing paths. We can approach this by creating a set of all cities that appear as starting points in the given list of paths. Then, we iterate through the list of cities that appear as destinations, checking if each one exists in the set of starting cities. The first city that does not exist in this set is our destination city. However, while this approach is simple to understand, it is computationally expensive. Checking membership in the set for each destination city involves O(n) operations, and since we repeat this for all destinations, the overall time complexity becomes O(n squared). Additionally, we need O(n) space to store the set of starting cities. This inefficiency makes the approach impractical for large inputs, highlighting the need for a more optimized solution. A more efficient solution leverages a set-based approach to optimize the search process. Here, the key insight is that the destination city is the only one that does not appear as a starting city. Using a set allows us to efficiently distinguish between starting and destination cities. First, we extract all starting cities into a set. Then, we iterate through the list of destination cities, checking if each one exists in the set of starting cities. The first city not found in the set is our destination city. This approach significantly improves performance because adding and checking membership in a set are average O(1) operations. Consequently, the overall time complexity is reduced to O(n), where n is the number of paths. The space complexity remains O(n) for storing the set, but the trade-off is worthwhile given the drastic improvement in execution time. This makes the set-based solution both efficient and scalable. Another alternative approach involves using two separate lists instead of a set. In this approach, we maintain one list for all starting cities and another for destinations. To find the destination city, we iterate through the destination list and check if each city appears in the starting list. The first city that does not appear in the starting list is identified as the destination city. While this method avoids using a set, it is computationally expensive. For each destination city, we perform a linear search through the starting list, resulting in an O(n)² time complexity. The space complexity remains O(n) for storing the lists. However, the inefficiency of this approach, especially for large inputs, makes it less desirable. The linear search through the starting list for each destination adds significant overhead, demonstrating the limitations of this method compared to the optimized set-based solution. The chosen strategy for solving the problem is the optimized set-based approach. This decision is based on several key observations. First, the destination city is guaranteed not to appear as a starting city. Second, using a set allows us to achieve O(1) average time complexity for lookups, making it far more efficient than alternatives like lists. Third, the problem constraints ensure a single path graph, meaning there will always be one unique destination city. The realization that a set could streamline the solution was the turning point, as it combines simplicity with efficiency. This approach ensures linear time complexity, which is crucial for handling large inputs, and the implementation is straightforward, reducing the likelihood of coding errors. While the use of extra space for the set is a minor trade-off, the benefits in terms of speed and clarity far outweigh it. Overall, the set-based solution is the optimal choice for this problem, offering the best balance between performance and simplicity. In this problem, we are given a list of paths where each path is represented as a pair, A, B. Here, A is the starting city and B is the destination city for that path. The goal is to identify the destination city that does not act as a starting point in any of the given paths. To solve this, we can use a brute force approach through iterative search. First, we extract all the starting cities by traversing the list of paths and adding each starting city to a set called start_cities. This is because the destination city cannot appear as a starting city, so isolating the starting cities will help us narrow down the search space. Next, we look at the destination city in each path and check whether it is absent from the start_cities set. If it is not found in the set, then that city is the destination city. This approach leverages the problem definition to systematically identify the target city efficiently. Once we identify a city that is not present in the start_cities set, we can confidently return it as the destination city. This is because the problem guarantees that there will always be exactly one destination city. Using a set for storing starting cities makes the algorithm highly efficient, as set lookups have an average time complexity of O(1). This avoids the need for nested loops and unnecessary comparisons that would occur with list-based lookups. Furthermore, since we are guaranteed that there is one and only one destination city, we can terminate the search as soon as we find it. The algorithm makes two passes over the paths, one to construct the set of starting cities and another to verify the destination city. Thus, the overall time complexity is O(n), where n is the number of paths. This efficiency is a key strength of this approach. To implement the algorithm, we use two main data structures. First, we use a set called start_cities to store all the cities that act as starting points. This allows us to perform constant time lookups to determine if a city is a starting point. Second, we work directly with the input list of paths, processing it sequentially without any modification. This ensures the algorithm remains both simple and clear. Let's walk through an example. Suppose the input paths are A, B, B, C, C, D. In the first step, we extract all starting cities. For the path A, B, A is the starting city, so we add it to start_cities. For B, C, we add B. For C, D, we add C. At the end of this step, start_cities contains A, B, C. These are all the cities that act as starting points in the given paths. Now that we have the set of starting cities, we can find the destination city by examining the destination city in each path. For the path A, B, the destination is B. Since B is in start_cities, it cannot be the destination city. For B, C, the destination is C, and again, since C is in start_cities, it is not the destination city. For C, D, the destination is D. Since D is not in start_cities, it is the destination city. Therefore, we return D as the result. To analyze the complexity, the algorithm performs two passes over the list of paths. Extracting starting cities requires O(n) time, and checking destination cities also requires O(n) time. Thus, the total time complexity is O(n). In terms of space, we use O(k) additional space for the set start_cities, where k is the number of unique starting cities. When applying this algorithm, it is important to consider edge cases. For instance, if there is only a single path, such as A, B, the destination city is simply B, as there are no other starting cities to compare. Another scenario involves multiple paths ending at the same city, such as A, B, C, B. Even in this case, B would still be identified as the destination city, as it does not appear as a starting point. For larger inputs, such as a list with up to 10 to the power of 4 paths, the algorithm remains efficient due to its linear time complexity. This ensures that it can handle substantial datasets without performance issues. These considerations demonstrate the robustness of the algorithm across a variety of input scenarios. This implementation solves the LeetCode problem destination city using a straightforward approach. The function desc_city takes a list of paths, where each path is represented as a pair, A, B. The goal is to find the city that only appears as the destination, B, and never as the starting city, A. 1. Step 1. Extract starting cities. The first line of the function constructs a set of all starting cities using a set comprehension. By iterating over each path and extracting the first city, A, we efficiently collect all cities that serve as a starting point. Using a set ensures that lookups for starting cities are fast. 1. Complexity per lookup. 2. Step 2. Identify the destination city. Next, we loop through all paths to inspect their destination city, B. For each destination, we check if it exists in the starting_city set. If the destination does not appear in the set, it means that city is the final destination, and we return it immediately. 3. Edge cases. If the input is empty, no paths, the function will return none, which is an appropriate behavior for invalid input. The assumption is that there is always exactly one valid destination city as per the problem constraints, so further validation is unnecessary. This approach is efficient as it processes the input in two passes, one to construct the set and another to find the destination, resulting in O(n) time complexity, where n is the number of paths. The space complexity is also O(n), due to the storage of starting cities in a set. This is the Java implementation of the destination city problem from LeetCode. The logic mirrors the Python solution, where we first collect all starting cities in a hash set and then iterate through the paths to find a destination city not present in the set of starting cities. Key differences include the use of Java's collections like list and set, explicit type declarations, and the structured class definition. To solve this problem, we start with the input paths, which in this case are London, New York, Lima, and Lima, Sao Paulo. Our goal is to determine the destination city, which is the city that does not appear as a starting point in any path. First, we extract all the starting cities by taking the first element of each path and storing them in a set. This gives us the set, London, New York, Lima. Next, we loop through each path to evaluate the destination cities. For the path, London, New York, the destination is New York, which is in the set of starting cities, so we continue. Similarly, for New York, Lima, the destination Lima is also in the set. However, for the path, Lima, Sao Paulo, the destination Sao Paulo is not in the set of starting cities. Since Sao Paulo is not a starting city in any path, it must be the destination city. We return Sao Paulo as the final output. In this example, the input paths are A, B, B, C, C, D, and D, E. Again, we aim to identify the destination city. First, we gather all starting cities by taking the first element of each path and storing them in a set. This results in A, B, C, D. Then, we examine each path to identify the destination city. For A, B, the destination is B, which exists in the set of starting cities. Similarly, for B, C, the destination C is also in the set. For C, D, the destination D is found in the set as well. Finally, for D, E, the destination is E, which is not in the set of starting cities. This means E is not the starting point of any path, so it must be the destination city. We return E as the final output. Here, the input paths consist of a single path, City 1, City 2. Once again, we want to determine the destination city. To do this, we first collect the starting cities by extracting the first element of the path and storing it in a set. This results in City 1. Next, we evaluate the destination city by examining the single path. The destination here is City 2. We check if City 2 exists in the set of starting cities, and it does not. Since City 2 does not appear as a starting city in any path, it must be the destination city. Therefore, we return City 2 as the final output. To evaluate the time complexity of our solution, we break it down into two main steps. First, we create the starting_city set. This involves iterating over all the paths, extracting the starting city from each path using path 0. Accessing path 0 is an O(1) operation, and since there are n paths, this loop takes O(n) time. Constructing the set from these n elements also requires O(n) time on average, thanks to efficient hash-based operations. Next, we iterate through the paths list again to find the destination city. For each path, we check if the destination city is in the starting_cities set. Membership checks in a set are O(1) on average, so this loop also runs in O(n) time. When we combine these two steps, the total time complexity is O(n) plus O(n), which simplifies to O(n). This linear complexity ensures the algorithm scales well as the input size increases. Now, let's analyze the space complexity of the solution. The primary contributor to space usage is the starting_cities set, which stores all unique starting cities. In the worst case, where all starting cities in the paths list are distinct, this set will contain n elements, requiring O(n) space. The input paths list itself is part of the problem's input and does not add to the algorithm's space usage, so its contribution is also considered O(n). Beyond that, the algorithm does not rely on any additional significant data structures. Temporary variables like destination and path occupy constant space, which is O(1). Therefore, the total space complexity is determined by the space for starting_cities and is O(n) overall. This means the algorithm is efficient in terms of memory usage as well, scaling linearly with the input size. Now let's consider the best, average, and worst case scenarios for this algorithm. In the best case, the destination city is found after checking the first path. However, even in this scenario, the starting_cities set must still be built first, so the time complexity remains O(n). In the average and worst cases, the destination city is found at the end of the paths list or it doesn't exist at all. Regardless, the algorithm performs O(n) operations in every case. When we compare this to a brute force approach, the advantages of the optimized solution become clear. A naive method might repeatedly iterate through the paths list to check if a city is a starting city, resulting in a time complexity of O(n²). By using a set for the starting cities, we reduce membership checks to O(1) on average, significantly improving the overall complexity to O(n). This improvement highlights the efficiency of the optimized approach. Finally, from a mathematical perspective, both iterations over the paths list are linear, and the space complexity is dominated by the starting_cities set, which is O(n). In conclusion, this solution is both time efficient and space efficient. With a time complexity of O(n) and a space complexity of O(n), it is well suited for handling large inputs. By leveraging efficient data structures like sets, we ensure that both operations and memory usage remain linear, making the algorithm robust and scalable. Common mistakes often arise when solving the destination city problem, and one frequent issue is not accounting for duplicate paths. For instance, if the input contains duplicate routes like A-B appearing multiple times, some solutions may mistakenly overcount the outgoing or incoming paths. To avoid this, you can use a set or a dictionary to ensure that each path is processed uniquely. Another common pitfall involves misinterpreting the problem statement itself. Remember, the destination city is defined as the one with no outgoing paths, not necessarily the last city listed in the input. Always take the time to carefully read and understand the problem requirements. Finally, inefficient checks for outgoing paths can significantly impact performance. A brute force approach that repeatedly scans the list of paths for every city can lead to O(n)² complexity, which is not ideal. Instead, you can optimize by constructing a set of cities with outgoing paths in a single pass and comparing it against the full set of cities to achieve better efficiency. Another challenge involves handling edge cases effectively. For example, scenarios such as having only one path, circular paths like A-B, B-A, or cities with no incoming paths can lead to incorrect results if not accounted for. It's important to test your solution against these scenarios and handle them explicitly. Additionally, some solutions may fail due to not verifying the inputs. Assuming the input is always well-formed, such as paths being valid or structured correctly, can result in runtime errors. To address this, validate the input structure and implement safeguards to handle unexpected or irregular cases gracefully. Proper handling of both edge cases and input validation ensures a robust solution that works under all conditions. To excel in interviews, it's helpful to recognize patterns that simplify the destination city problem. The key insight is that the destination city is the one without outgoing paths, and leveraging data structures like sets or dictionaries can streamline your logic while reducing runtime complexity. Brute force methods might work for small inputs, but optimizing to O(n) is critical for competitive coding and interviews. Always aim to demonstrate your ability to optimize when discussing solutions. Additionally, edge cases should never be overlooked. Take the opportunity to ask clarifying questions about constraints such as duplicate paths, empty inputs, or cyclical paths. These questions not only help refine your understanding but also showcase your attention to detail. Finally, communicate your thought process clearly. Explain why you're choosing specific data structures, like sets for quick lookups, and discuss the trade-offs between code readability and efficiency. This approach demonstrates both technical skill and strategic thinking. The concepts in the destination city problem are closely related to a few other problems, which can help you deepen your understanding. For example, LeetCode 997, Find the Town Judge, also involves identifying a node based on incoming and outgoing edges. Another related problem is LeetCode 841, Keys in Rooms, which uses graph traversal to determine if all nodes can be visited. LeetCode 1557, Minimum Number of Vertices to Reach All Nodes, focuses on identifying source nodes that have no incoming edges, which is essentially the reverse of the destination city problem. Lastly, LeetCode 210, Course Schedule 2, introduces topological sorting in a directed graph, offering a more complex variation of path analysis. Exploring these problems can help you spot commonalities in graph-related challenges and strengthen your problem-solving skills. There are multiple approaches to solving the destination city problem, each with its own trade-offs. A brute force approach involves iterating through each city and checking if it appears as a start point in any path. While this method is simple to implement, its O(n)² complexity makes it inefficient for larger inputs. A more optimized solution is the set difference approach. Here, you create two sets, one for all cities and another for cities with outgoing paths. The destination city can then be found as the difference between these sets. This method has a time complexity of O(n) and is much faster, though it does require additional space for the sets. Another alternative is using a dictionary to map cities to their outgoing counts. This allows you to directly identify the city with zero outgoing edges. While this method also runs in O(n), it may involve slightly more memory overhead than sets. The choice of approach often depends on the problem constraints and whether additional metadata about the paths is needed. Great job! Today, we covered the destination city problem, explored its solution, and discussed key takeaways. Remember, understanding the properties of nodes in graphs is essential for problems like these. Thank you for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!